Alfonso, welcome back.
Hi, thanks for inviting me again.
Yeah. You saw the numbers, right? My performance numbers. Is my machine faster than yours?
Yes, you have like a M3 Mac?
Yeah.
Okay, yeah. So these Macs have more bandwidth, memory bandwidth, and it shows.
Okay. Because what I did, I tried the Llama 2 and 3. And 3 is more interesting because I was able to chat with it, like with ChatGPT. And I think, was roughly 10 tokens per second, right? This was the performance on 9 or something. How fast is it on your machine on an Intel?
So in the laptop, I get like maybe 7 tokens per second. I have a very, very good laptop. And on the desktop, I have a workstation. I think I got maybe 8 tokens per second. So I think the Mac has an advantage.
Yeah, but it's still the same ballpark, right? It's a roughly.
Well, so if you run it on a Raspberry Pi, for example, I think you get like 1 token per second, which is fair,
Yeah, but you couldn't even start Teams on the Raspberry Pi, right? So.
Yeah, that's right.
Yeah. Okay. So crazy story. So back then we talk about Llama 2, and then meanwhile you published Llama 3, which I also tried, and yeah. So first, did you got any feedback about that? So something happened, or?
Well, yes, I got some feedback, private feedback, and some on Twitter, people were like, "Yeah, it's so cool, and can I do this? Can you like integrate it with LangChain for J and stuff like that?" So yes, so it's a very nice toy project, let's say. So it's because you can just use the models that are out there. It's not like as custom as the previous one. So it's just a regular, similar to Llama CPP. Just download the model from Hugging Face, run it, chat with it, and I think that's also very nice. So I got some feedback. For example, one of the feedback I got is that it is slow on some machines, and one of the reasons is that people use GraalVM as the main Java distribution, and the GraalVM doesn't support yet the vector API. But this is something we're working on. We hope at some point to get not only the JIT mode, but also maybe native image to run a subset of the vector API enough to do these multiplications pretty fast.
Okay, so maybe we we already had a chat about that, the Llama 2 integration, but maybe we should recap some of the things. So what you did is, so what is Llama? Llama is a model from Meta, so Facebook company, and it is open source. And a model is just a set of numbers, and it is roughly 4 gigs or 8 gigs on disk. And you achieved the following. So you used JDK21 and a preview feature called Vector API, and you could natively read this the model, and you got the inspiration from the Llama CPP from Andrei Karpathy. What he did the same in C, and you ported the C to Java, and this is why it's called Llama 2 Java and Llama 3 Java, right? So this is the story. So, and the surprising thing is, or the amazing thing is that without any additional dependencies, you can just run the inference. It means run inference means you can use the model locally without JNI, without anything, just with plain Java 21. And in fact, I was able to use it without any compilation with Java 21. You can just say Java without anything, and it just runs without Java C, without class paths, without anything. So I would say this is maybe the most seamless model inference on planet right now, I think, right? Because it cannot be any easier than this.
Right. Yes. And so in the meanwhile, because the last podcast was like 2 months ago,
Yeah.
Every weekend or almost every weekend, I added new models. So it's not published yet, but I have Mistral running. I have Quen from Alibaba. Maybe we can talk a bit about the Quen models because it's very interesting because they have smaller models, basically you can run it in lower specs, so it has more token per second. I also ported the Llama models from Google, and there's also the Phi models from Microsoft. So basically, I have all these models running in a similar way, right? So I have like a Mistral.java, I have a Phi3.java, I have a Quen2.java. So all these other models are alternatives. Llama was the first one, and you may think that these ones are very different, but actually they are not. So it's like they are cousins. So you take the same computation graph, you add a little tweaks here and there to adapt to the specifics of the new model, and then you can run the models from all these other vendors. And they all have their strengths and the limitations. The license may be not fully commercial, so maybe you cannot use it for commercial purposes. Other models allows you, right? But maybe the model doesn't have certain features and so on.
Mm-hmm. So first, I also got some feedback because I created a screencast about that because I like it and to promote it a bit. And they say, okay, but you have, if you use Llama, if you use Meta's Llama, you have, to have an attribution. And I say, yeah, but the Llama is just the first step. But what we learned the last time is that the Llama model, because it's open source, it was like the first model which somehow is used as a convention for the format. So for you, you said last time Mistral and the others are similar to the Llama model, so you can use exactly the same approach and integrate the other models. And this is what happened, right?
Right. Correct. So the original Llama model, so Llama 1, was so good that actually you had to do so very little. So I don't even know why these other companies tried, because it's basically the same thing, just minor modifications that you may see, but maybe this is not necessary. But anyway, so once you have exactly in the end, so all you got is the same structure, because you have a number of layers, and on every layer you have this transformer block. So the attention, so it's the same graph with very, very, very minor additions. Mm-hmm. So, and all these companies just literally just copy paste the model because it's so good. There's really not much to add there.
Mm-hmm. So they're copying the Meta's model and extending on it, right?
Right, exactly.
Mm-hmm. So the question is, what you did exactly to port Llama 2 to Llama 3?
Well, so the previous repo worked with custom format, mm-hmm. Because it's based on the code from Andrej Karpathy, and he had the custom format where you really only read floats, so 4 bytes per bit, and that's it. So it was literally not very compact. No quantization means that the models were very large. Anyway, this was enough for the smaller model. So because in the repository he had these tiny Llama, tiny stories models were that to generate stories based on a prompt. And these ones run fine, right? But in the moment because I did convert, at the time was still Llama 2, the model, the 3 was not yet out. I converted the Llama 2 model to this format, and then I got like 1 token per second, because mm-hmm. of course every weight was float and was super slow. But then Llama 3 came out, and I came to the podcast, and I got this idea that, okay, maybe I should try to run it, because and I implemented all the logic to read from this GGUF format from Llama CBP, which is the de facto, the open source format for the models. It is not very hard. The format is very well specified. It's very friendly, so it's not like JSON or anything. So you really have like some key pairs, like this. So for example, the model name is this one, the model architecture is this one, the tensors or the weights are in this offset from the file, so you can memory map it. So it's a very straightforward, very well documented format.
Is it a standard or quasi-standard, or what is it?
I wouldn't say standard. So they have a spec, a very well written, well defined.
What is the name of the spec? What is?
It's called GGUF. I think it's like
okay.
GG Universal Format or something like that.
Okay.
There have been a few iterations. I think now it's version 3. But the thing is that I think I have like maybe 100 lines or maybe a bit more to read this format, which is very well typed and very nice. And once you can do that, basically you can read whatever model you find on Hugging Face.
One idea immediately. Wouldn't be a good idea for you, if you have time, of course, to create a JSR on JCP, Java Community Process, just to read the GGUF, and you have the reference implementation, and
Right.
others could be.
Right. Yeah, of course. I mean, I think I haven't seen any other parser of this format besides the Python one. And they have one in C, of course, and then there's one in Python, but I'm not sure the details. But I haven't seen any other parser of this format in, I don't know, C# or JavaScript or whatever. So basically, yeah, I think it's the only one in Java that I've seen by now. So what do you mean with a GSR? Like a way to standardize the implementation or the
There's a
reader?
Java specification request or JCP, Java Community Process, which is larger than Java. So in Java, we have JEPs, and the JSR was something like JPA, Java Persistence API, or something like this. So this is like a bigger spec. And the idea would be, to have, if we say this GG is a quasi standard, not really, we could say, okay, in Java, the interface would look like this, and you could provide your implementation to the interface, and other contributors could have, different parsers which will compete with yours. This would be the idea.
Right.
So to make it more credible. Because now, besides I recorded a video and we spoke about that, no one knows about that. So this could give the entire thing more visibility. And yeah, just an idea. But the JCP, it was started by Sun, and now Oracle is the steward. So it is independent, but it fits well with the entire thing. It was just spontaneous idea. It's say, okay, standard is the first one, but so the others are not parsing the model. What they are doing then? I assume Python is too slow to read it, right?
Well, not really, because the model is mostly, I would say, 99% weights. So, and these weights are just a blob in the file that you memory map. So you don't have to read it; just memory map it. So the way the format consists, so is you have at the beginning some metadata. This metadata, for example, includes the vocabulary of the model, so all the tokens, and some additional metadata, but it's fairly small compared to the.
What do you mean
size of the
vocabulary?
model.
You mean the real tokens? What's inside? Is that text? Or
Yeah, exactly. It's like, for example, token number 4 is the word "the" or and so on, right?
Okay.
So they embed the vocabulary of the model inside the GGF format, and I think this is a very clever move, because before there's a myriad of different ways to tokenize, and actually tokenization is a huge, let's say, burden, because it's always done differently. It's not compatible. It's on the implementations are mostly in Python. It's very hard to find an alternative implementation in Java. So I basically had to write my own, and there's always these subtle details that the companies or the people that train the model think they are very clever to do certain things, but actually they just kind of customize the whole thing, so the whole inference, because now you depend on a custom tokenizer, and the tokens it's really that having different tokens is not a problem, but having a difference in the process, how do you tokenize, so encode or decode the input and the output of the model, it adds a burden. So what they did is the Llama CPP guys, they tried to kind of standardize somehow the vocabularies and the tokenization. So they include the vocabularies, they include the type of tokenizer they have, and I think that's very nice, because kind of like forces many of these companies or people that train the model to actually think, okay, maybe we should just use a standard way of tokenizing, and that's it. So yes, so the part that is most complicated is actually, that takes more time, is to actually read all this metadata, parse it, and then the way to just memory map it. It just costs nothing.
Yeah, except the call to the map, right? So I mean, in Java it's natively. In Python, I don't know how they are doing, but they have to some access the.
Well, I guess that they will call to C or something.
Yeah, exactly.
You wouldn't yeah, you wouldn't read it, or I don't know.
Yeah.
Maybe they for sure they have something native going on.
Yeah. Okay, so you memory map that. So it means it is mapped. Yeah, what's the name say? So not like you are reading this, parsing it. You're mapping this to memory and accessing this on demand. And this is very fast way in Java, to access a huge amount of data. Most of databases are using the same approach or trick. Okay, so and you say that the format changed between Llama 2 or Llama 3, or your approach is better right now, more close to Java CPP, right?
Yes, correct. So now the thing, so the implementation I have in Java, it's more capable. So it's not, before was you were forced to use a specific format, very like handcrafted format, and now it can do much more. I have several tokenizers, so basically all the models I supported, I implemented this small variations in the tokenization. So and it's not that hard. It's just like small detail that you messed up. For example, I have this model that it cannot print emojis because the tokenization is just not correct. For example, just a small thing that is missing is that in some cases the emoji doesn't work, or the Chinese characters don't work because the encoding is not properly handled and stuff like that.
Yeah. By the way, I had some automation, and I also cannot read an emoji, so they're just strange characters without Llama, right? So emojis seems to be a special. So some issues, just too lazy. Okay, so what it means, what you are doing, you are reading the metadata, and depending what's in the metadata, you're picking the right tokenizer, right? So as understood, it's like almost like not factory, similar to something. Okay, I have this configuration, now give me the tokenizer, and you have a pluggable tokenizers, so you can react to multiple models.
Correct. So yeah, exactly. That like I think 2, maybe 3 different tokenizers with different configurations, because of course, and yeah. So, and as I mentioned, it may work because still the tokenization process may differ. For I don't really understand what they were thinking, but why not just stick into something like like a standard tokenization way? But anyway, just that's
this is how Java was at the beginning. This was we didn't have JDBC, so to access two databases, you had to rewrite completely your code. Whatever, there was always, and this is, I think, now we are in the same stage in the AI. But we had what we had Java already lessons learned. So we went through the cycle. So it means now we could actually, from our experience, make it better. And this is what excites me about AI and Java, because with the experience from the past, we can actually create a decent thing. So what you said is, no, there are no parsers in Node.js and Python, and you created one, and now it is already pluggable, the next version. This is actually a great thing. So, and what you are saying is that the Mistral and the others have the same format, but they use maybe different tokenizers. So what you have to do, the metadata parser is the same, and you are just, need a Mistral tokenizer or whatever is inside, and then you can integrate very easily Mistral, right?
Correct. So, but the tokenizer is only one part of the equation. So for the whole thing to work, because the way you talk to this model, so what you write your prompt. So you have to write your prompt with special tokens to say, okay, here's the prompt. Now is the turn of the model, and let it run the inference, right? So this is also completely different in most models. Mm-hmm. So literally, and this is even more custom, because there's really no specific. There's one format that tries to be kind of like a generic enough, but no, I think like it's very little used, so nobody uses it. And every model has its own way of constructing these prompts and the way you have to ask the model for the. So this is also very annoying. But again, so for example, in LangChain4j, I think they had this issue. So, I mean, they don't have it because they just a common API. Yeah. But every backend, I guess, needs to be aware of the way to prompt the model.
Yeah, even I had the issue. So I use Bedrock a lot, and I remember at the beginning there was like a user message, and then we're like, you need some new lines. And then they change. Maybe this is what you talk about. So this was the complete different way how you separate user message from system message. And now exactly. More or less, I think it's called the message API. I don't know whether it is as low level that you see this. and the message API is more like, more like key value pairs. So I can say this is the user message, this is the system message, but I don't have, to have strange, markers.
Exactly. So
Yeah.
that's completely custom. So, and as I mentioned, if you miss an end line, maybe the whole inference is kind of incorrect or
Yeah.
messed up in some weird way, because the model was really not expecting, or was expecting to have like 2 new lines or something like that.
The same fun as encryption, if you do one small
Exactly.
everything
All by one, and it's all like, garbage.
Yeah. Okay. Cool. So I would say this is a missed opportunity for Llama and Facebook, right? Because they could try to standardize it as well, and then everyone will have to implement the Llama, because now it is the only more or less complete open source model, which with really high quality. Mistral is catching up, but Llama was, I think, one of the first or the most popular one. So they could actually say, okay, this is the format, and this is open source, this is the spec, and then it would be interesting what happens, right?
Yes. So one of the incredible things about this model is that they are kind of simple. So because you would expect this thing to be super complex AI, or like some super complex systems, but actually it's just you multiply matrices and that's it. So there's really nothing there that you cannot. So everyone can see, can inspect what's there, and there's really nothing that complex. And I think actually this simplicity is one of the main strengths for these models, because if you can achieve this level of I don't know, success, let's say, like, so these models can are very powerful with this simplicity. I think that's one of the key points why these models kind of took over the world. I mean, at least the smaller ones, because you can have the bigger ones. You need like several GPUs to run, but if you can run it on your machine and it doesn't really require any like impossible to digest complexity, it's actually a very simple algorithm. Then there's something there that is actually quite magic. It's okay, like maybe this it can only get better from now on, because the core at the core it's just a very simple algorithm.
So what you had to do is you had to make the tokenizers pluggable, and then the prompt parser, or how to call it, prompt
Correct.
interpreter, is also model dependent, so it's also pluggable in your case.
Yes, correct.
Okay. So what else you had to do? Is both?
Well, I think if you get the tokenizer and the I call it the chat format, but
Chat format. Okay. Yeah,
it
right.
varies. I think you get everything. So the other thing is, well, of course, adapting the inference part, because as I mentioned, every different model, except for example, Llama and Mistral is the same. So they do not have to do anything on the inference. It's exactly the same algorithm. But if you go to Quen, for example, from Alibaba, they add like some extra ads in the so they have extra operations in the inference graph. And I mean, it's a very tiny change, like 2 lines or 3 lines, and that's it. But still, it is there. So you have to add it. Otherwise, if you don't add it, of course, the model will completely drift and start like outputting gibberish. But and this is actually quite tricky, because what I do usually is I go to the Python sources, and then I go to Llama CPP to see what's the difference between the source model, for example, because I start with one, let's say Llama or whatever, and then I start to adding this additional these additional operations to the models until I get something that actually, and then I need to evaluate. Okay, like just if you make it the model to inference, I don't know, 8,000 tokens, does it have any gibberish there? Is it like it's the text is correct? Is it preserves some sanity? It doesn't go crazy. So yeah, so that's kind of the process. It takes a bit, but it's not. So once you do it once or twice, then it's almost trivial the third time.
So you studied Python and the CPP code to see what they are doing with the Alibaba model, right?
Yes, I had to learn some PyTorch to realize like what's going on, because as I mentioned again, so for example, they have these encodings for the tokens. So the way the tokens are encoded, they're encoded in a way where the distance between the tokens is relevant. So in the very early days, the tokens were encoded literally with the position. So you position 1, 2, 3. But the problem with this, that then what you really care is the difference or the distance between two pair of tokens. You really don't care if this token is the first or the third. You only care about these tokens come before this one or after this other one. So they have this encoding, and again, they change it. So the way they do this encoding is basically the same algorithm, just a little changes, like let's do it this other way or this other one. Anyway, so these tiny little changes are very annoying, but I mean, once you do it once or twice, I think it's just the same for all the other models.
Is a token a float?
A token, so for now, it's an integer. So an integer
okay.
that is mapped to, well, it is mapped to a string, and the other way around. But what you get from the model is one big array with the floats. So basically, the probability that a specific token is the next one. So that's the output of the model, and then you need to pick. And then there's these tricks, for example, this famous thing called temperature, which is really at randomness to the selection. So you could always pick the token with the most probability.
The zero temperature, right?
Yeah, exactly. So it means nothing, but so it means that like do not add any randomness. Just pick the token with the most probability.
And you implemented the randomness, or is it a
Yes.
model? Okay.
So I actually, you can, this is a custom thing. You can do whatever you want. So basically the model literally gives you a big array with probabilities, and you need to pick the next token as you see fit. For example, and there are many ways that like you can, I implemented a few, this called samplers. For example, I want to sample a token from the, I don't know, 5 topmost probable tokens, for example. And something like that. So there are a few different algorithms that give you different characteristics, but that's it. So, and this is not particularly has nothing really to do with the models themselves, but you can customize it after. So, for example, the Llama CPP has this nice feature called like the grammars. For example, you can force the model to. So you don't force the model because the model will give some probabilities, and you force the tokens that can be valid JSON. So literally you follow the grammar. So you really kind of discard a bit the probabilities, and you really try to pick the next token that kind of fits the JSON grammar. So you, for example, your model outputs a valid JSON, for example. Yeah, that's one of the sampling tricks you can do, for example.
So you also have pluggable samplers. So you have pluggable chat formats, tokenizers, samplers.
Yes, correct.
And the Alibaba trick, how to call it, if there are specific formats, or what you did, the custom operations, or
well, it's very simple. So they add, let's say, like, so they found out that if you do certain change in the model graph, for some reason they find out that you get, I don't know, maybe like 1-2% improvement in something, and they just leave it there. So they just, okay, let's use this because it gives better scores in something.
Okay.
Or for example, but this is really nothing that changes the entire structure, just very minimal changes. The global structure of the transformer, the attention, is basically the same.
And so you have the temperature, and there's another parameter. So temperature is the probability, and the other is the breadth, right? So there's what is called the other parameter? It was temperature and the other one. So there's always...
Well, there's something called top P.
Yeah, top P, exactly. Top P.
So top P in this case means that I will sample only from the 5%. So you can, it's a float, you can put it like, or I will only sample, or I will only take into account the top X% tokens in the probability. So I would literally just filter out the tokens with that are not the top 5%, and then only pick in some way, because then from that 5% that remain, you can also like apply another sampler, right? So from these ones, I will, for example, let me sample a token from these ones depending on the probability of the token. So still the tokens that have more probability still get more chance to be selected and so on. But anyway, so you can compose them, you can change the order on which this sampling algorithm works. But I think that just this is something you can do regardless of the model you're running.
Yeah, pretty cool. So with that trick, you can basically adapt all models which are similar to Llama, right?
Yes, yes. So as I mentioned, all these other models, they are quite similar, right? They're like little changes, but they run all fine, and they have tiny differences. Maybe we can talk a bit about not only differences in the what they things. The training. You can see some weird and corny cases where you ask something and they ask in some unexpected ways. Let's say.
Yeah, let's talk about the differences. So what you learned about the difference about between the models.
Right. So it's very funny because this is my personal experience.
Yeah, sure.
Maybe if somebody else tried some other I don't know questions or prompts or tasks, then maybe you get different results. But for example, one of the problems with the models is that they can produce, or they can give you let's say instructions to do illegal things, right? For example, how do I build a Molotov cocktails or stuff like that. So the companies added some filters. Filters means that they to try to train the models to refuse to answer these kind of questions, right? So I understand this is a good thing, right? And it has to be done very carefully, because otherwise, if you go too much, then the models start to refuse genuine questions. So, for example, if you ask some of this model, "How do I kill a child process?" He would say, "No, I cannot tell you how to kill child processes. Killing children is bad," for example. This is one of the prime examples where you find this like a bit ridiculous. But if you add more context to the prompt, you say, "Oh, how do I kill a child process on Linux? Give me the command." It will say, "Oh, sure, you can use kill -9 the PID and something like that." So it's not that the models do not really know. It's just that they were trained, or they were in a way that maybe it is too broad, right? So they have too little context to, and this applies to basically all models, right? So they have these safety measures that some models are really, really annoying in this aspect. So they really refuse many things. So if they don't like what you're writing in some way, they say, "Sorry, I can't help you because blah 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 blah." Some ethics.
Which one is most restrictive?
I would say the early Google models were very, very annoying. I think that the new one is called Llama. The Llama 2 is better, but the first one really, really didn't like any weird questions, and didn't really like to be corrected. So if you, and that's also like kind of their own, right? If their own personality, you can say, if the things have something like that, in the sense that other models will quickly backtrack, say, "Oh, sorry, blah, blah, blah," and then just kind of try to give you another answer. But this Gemma was kind of stubborn, say, "Oh, no, sorry, so it is what it is, and here's the answer." And again, sorry, that's all you get. And
you're speaking about the Gemini models, right? So
not really. So they have the Gemini, which is our closed source, and they have this Gemma, which are open source.
Okay.
So I think the new one is very good. So they have they still, of course, all these models have this safety post training thing, which is, I think, is good. But you have to be very, very careful. How far do you go with this? In order to not to dwarf or the model capabilities on its own. So one more thing. So there are more models. For example, the ones from Alibaba. Usually, Llama 3 is 8 billion parameters. So it's a rather, like, I mean, it runs locally depending on your hardware, but it's a rather large for some machines. There are other models that are smaller. For example, Alibaba they have in 0.5 billion, so literally 500 million parameters, which is very, very, very tiny. But at the same time, this model is not very smart. Very smart. So it's like talking to a hamster in some extent. So you can make it to do like basic tasks, and it kind of has certain understanding. But it is you can you can use it only for tasks that for its own like weight, right? You cannot use it for anything complicated, and so on. So they have one another model is like 1.5 billion, right?
What could be such use case for such a model?
Something really simple, for example, that you really need the performance. So imagine you have a Raspberry Pi and you want to, I don't know, like something as simple as maybe, and it doesn't have to be that precise.
Hmm.
Let's say, for example, you can give like simple instructions. I don't know, for example, like this sentiment analysis, that you can do it.
Okay.
For example,
Okay.
you get a tweet. I say a tweet because it's like, I
Hmm.
mean, you can have like large tweets these days, but you can say a tweet and say, okay, tell me like if this tweet is a positive or negative, or or
Oh, okay.
extract some
Got you.
information about the tweet. So I think this kind of, I mean, so if you really the problem with the more complicated tasks is that where you ask the model to follow certain steps. Okay, take this text and extract me this information as a JSON in this format. If you start to adding such complex instructions, then these tiny models, then they cannot
But you could
catch up.
invoke the tiny model a couple of times, right? So you could chain them.
Well, yeah, these tiny models runs very fast, so
So,
you
but you can say,
can.
instead of giving them instructions, you can say, parse it, you get this back, and then with the result, you can call it again with, and say, okay, now you have a JSON, do something with it, right?
Well, but that's the problem. So I don't think they are like even smart enough to follow JSON.
Ah,
So
okay.
that's
Then
what
it's
I
a
meant.
problem. But you could.
They could,
My
they
question in
could.
general is it a good idea if you have not so powerful model to call it multiple times instead, having a more complicated prompt, right?
Yeah, for sure, for sure.
Yeah.
I mean, that's what I'm saying. Like there's for example, another example where a smaller model will make sense is I mean, in certain tasks, for example, this autocomplete. So you're typing something in a search bar or something. Imagine I don't know, like a store, like an online store, where the terms you may search for are not semantically the same. So it's not like, because Elastic and all these Elasticsearch, all these other engines, you can phonetically index the terms. So
Hmm.
if you type something that is phonetically close, they still get it. But
Yeah.
sometimes you have a semantic term that is exactly the same, it's a synonym, but it's not searchable because the thing didn't know that about that specific term.
Hmm.
So grammatically it's correct, but just it's a completely different name to
Yeah.
what the actual store or the indexing was storing. So with these tiny models, you can say, hey, give me like, I don't know, 10 alternatives for this search term, and they will suggest you different variations, semantically valid variations of the search that may be useful to amplify your search, for example.
Thesaurus, right? So like, just give me the alternative words for this one, right?
Exactly, for example.
Yeah.
And
Okay. This is a very good point. This is actually a good, because it's search anyway. So if you see the results, nothing is problematic. Yeah. Yeah. Pretty cool. So I mean, you are crazy, right? So this is a huge value right now because, for instance, the Mistral is an enterprise model because, at least in Europe, because it was created, I think, a French one, I think, a French company, and this is a complete more as is more companies will trust more, the French open source model than a closed one US model. So I would say a huge step forward. So, what interests me, performance. So, is it a little bit slower than the C still, right?
yes, so there are a few reasons for that. So it's
Yeah.
not that um, one is the vector API. So
Hmm.
the vector API is still in preview, still, and it has some gotchas, like, like you would expect that if you write some code using the vector API, that it will perfectly translate to some vector instructions,
Hmm.
but that's not always the case. You have
Hmm.
to be very careful. Even if you're careful, certain shapes of code for some reason cannot be.
How you know it? You debug that or
You just run it and it's slow.
okay?
I tried to debug in some cases and I found like some workarounds.
Hmm.
But let's say, like, in an ideal world, what we should get is like you write perfectly valid code using the vector API without, you cannot store a vector in a field. You cannot. There are certain things you cannot do. Because otherwise the compiler just loses the ability to vectorize the code. But if you're very strict in the way you write your vector code, I will guess that the vector API and the compiler should guarantee to you that your code is going to be fast.
Hmm.
This is not the case in the current.
Hmm.
It is, let's say, it is very good because one of the cool things that you just write your vector code and it will compile it for no matter which platform or CPU you are. So ARM or well, this like maybe RISC-V in the future, or maybe there's already like a RISC-V port, but I don't know.
Maybe you should explain it. So the vector API means it translates to vector operations, which are a little bit different. So there's highly parallelizable operations, which run where actually on GPU?
In the CPU. So let's say like also the CPUs realize that many algorithm or computations you can actually speed it up because they do exactly the same operations many times. So and then they added what is called vector operations. So basically, you take instead of operating in one register or two registers, you operate in batches of, I don't know, 8 elements at a time. So you, for example, you do 8 adds at a time, and then it takes the same amount of time of like clocks in your CPU. So, but the problem with these operations is that they are custom to the CPUs. So, for example, x86, for example, have different subset of operations they can run, different like instruction sets, right? And the nice thing with the vector API is that they can target completely abstracted to you, so you don't really need to care. They will compile your vector code to the best possible instruction set that is available in your machine. So that, I think that's the very nice thing of the vector APIs, because otherwise, what happens now is that you need to have C files or some C++, whatever, some native code with all the operations you want. For example, in this case, this matrix multiplication, you have to write an implementation for the multiplication for every single platform. So, do you support AVX 512? You need an implementation for that using the specific instructions and so on. Oh no, you are a Mac and you are like a Neon operate instructions, and you need like to write again the operation for that particular case on the machine. And then the matrix of supporting different features and matching that to the actual CPU instructions is kind of messy. So with the vector API, which is still in it's a preview, it's a work in progress, is that you write it once as I mentioned, in a very strict way. So you need to be very disciplined the way you write your vector code, and then you get the speed up. So, and this speed up may be like 4x, 8x, which is, I think, considerable. So it's not something that you can just left aside. It's not like 10% or something. It's just something like really meaningful.
So we are speaking about SIMD more or less right now, right?
Exactly. SIMD.
Okay.
Right.
Why I got confused? Because I don't know whether you remember, but there was Pentium MMX.
Yes.
And the Pentium MMX introduced exactly that on Pentium. This was multimedia extension, which was SIMD. And what I thought is, because it disappeared at one point of time, that it moved to the GPU, but it moved to the CPU later. It became a part of the CPU, right?
Well, I think you have this demand from the software world, like you need to run some things on the CPU, and then the Intel and AMD, they just start adding instructions to accelerate certain workloads on their CPU. So this is kind of this balance, right? And I think SIMD was one of they were added for the multimedia, right?
Exactly.
But then someone realized that, maybe you can use this, to multiply matrices or to do crypto or to so to accelerate many other operations, and then that's how we end up with this actually fairly complex vector instructions, because today it's not only for like the small use case. It's a very generic general computation paradigm. So you can actually do like almost anything using vector APIs now. That's all the SIMD instructions.
But could the vector API could be also translated to GPUs, right?
I think the GPUs, yes. I think some GPUs also provide some sort of vectors as part of because it's the same principle. But so my opinion is that you already have a crazy amount of parallelization. So really, like, it's kind of, maybe you get 4x, 8x. That's good, but and the CPU, you literally have like one thread, and that's it. You really need to pack as many instructions you want. But in the GPU, you have like thousands of tiny threads, and then it's kind of like, why would you do that?
Well, why I'm just asking is because we could actually in future use the vector API to run it on GPU in theory.
Right. So that's the idea of Tornado. I think you can compile
Exactly.
certain GPUs support some sort of SIMD operations. I'm not entirely sure to what extent or this is complete, or so what's the actual feature set that is supported. But in theory, you could, yes. Actually, I think Tornado VM already supports some kind of vectorization for GPUs. So, but I don't know exactly how the details are. So basically, you write your code in Java using some types, like some vector types, not exactly the ones from the Java API, but some custom type from Tornado, and Tornado will figure it out and will translate that to efficient SIMD operations on the GPU.
Okay, so perfect. So, but even better because, yeah, of course, we run on a CPU, so it is more. You can run it on any machine. With GPU it would be a little bit more problematic. Okay, so the first reason why it's slower than C is because the vector API is not perfect, right? So yet, so it is a preview, but if it gets better, it gets automatically faster. Do you have a feeling how much faster could it get if you know?
Well, there. So one of the things is that the entire let's put it this way. So when you run inference on a token, so you try to predict a token, 90% of the time is spent multiplying matrices. So, and it's like shocking, right? It's like everything else, all the other operations you do, all the the softmaxes or the normalizations, all this stuff, just 10%. And in this particular case, it is in this way because Java is pretty fast. So everything else, Java can compile it properly and can do a fairly good job. But for the matrix, it's just a matter of sheer like brute power, right? So you really need to have a very specific, very fast routine to multiply matrices. And with the vector API, you can get some like the speed up, as I mentioned, but there are like maybe like 10% or 20%, or even in these new multiplications, they in Llama CPP, for example, they try to do these multiplications to be cache friendly. Or in the case you have like the prompt processing, where you can actually, you don't do a matrix vector, but you do a matrix. In that case, if your metric is small enough, they can take advantage of that, and if it fits in your L2 cache, then they can multiply the matrix faster. And so there's a few examples where I don't know how to exactly do that on the using the Java Vector API, because you really have very little control of what's going on, of what's being compiled under the hood. But probably it's something you can let's say envision in the future, to like you can have, okay, really think up to the hardware level. Okay, I want to really use this, run these memory operations and really on this shape, so I can know for sure that it will fit on the L2 cache and I can get the speed up and so on. So another area where the vector API can improve, and actually we've talked a bit in the GraalVM group to make it, is to guarantee that you get a speed up. So because as I mentioned, the vector API will compile as a best effort attempt, right? So it will try to give you some fast code, but it doesn't. So the compiler is not always able to do it. And I think one very nice feature will be either your code is fast, right, or you get an error. So sorry, your vector code cannot be compiled efficiently, and so on. So I think that will be a very nice feature, and maybe something that could be included with native image or something like that. So like if you have a snippet of vector code, then you have the guarantee that it's going to be fast because it's AOT compiled.
So this is actually good news. So it means we are as fast as C, but C can do more tricks because they are more low level. So they
Correct.
can. But how much slower are we now? 10%.
10%. As I mentioned, if you go like smaller models, where they can take advantage of the L2 of a few extra tricks, then maybe you get like 40% or even more. So the smaller the models, the smaller the matrices, the larger is the speed up.
Okay.
You're getting C versus the vector API.
Because the matrices are smaller and they can apply more tricks to fit it to L2 cache, which is, of course.
They have routines specifically tailored for smaller matrices.
Yeah.
So, which in the case of the Java API, we don't. But we could add like also oh, if the matrix is small, then I will do this other multiplication because it's faster,
Exactly.
and so on.
Okay, but it's not like the C is faster because of the algorithms. They are just faster right now because they can do more tricks, and you didn't optimize it yet in this. So
correct. So if anyone goes to the Llama 3.java and you go to the matrix multiplication, you will see like it's like less than 10 lines, maybe even.
Mm-hmm.
So it's a very straightforward dot product. So there's really nothing else trying to do tricks or to. So even the way the threads are, because we run in multiple threads,
Mm-hmm.
In the C, they kind of, okay, let's assume that the CPU is like a GPU and they distribute the thread and just there's no contention. So they have a lot of these things. But in Java, it's just like, oh, I have like n dot products, just run it in using like streams, parallel streams, and that's it. So Java will take care of all this for you. And I think that getting within 10% of native code is actually a very, very good result.
It's extremely good. So I was actually, it's a very good result. And I was just curious whether we can do something and whether you see something which you could optimize on the Java side. But yeah, this was the...
right. Mm-hmm. So by the way, on GraalVM, I think we are trying to get a subset. So GraalVM already supports a very small subset of the vector API. For example, you can run Mandelbrot and it will, compile properly. We're trying to get a small subset enough to run these matrix multiplications for the models. So let's say like the initial step will be the JIT, and again the next step will be native image.
Mm-hmm.
So and with the good thing that if you have some vector code, you will guarantee that it's going to be fast if you compile it with native image. But that's more in the future because native image requires more. It's more a complex thing to do with the vector API.
But native image doesn't have to be necessarily faster, right?
Well, I mean, there's no reason why it shouldn't be fast or the same, basically, because you see the vector operations, just translate them.
But there's nothing to do for the JIT optimizations, you mean,
exactly.
Right?
So literally, and usually, as I mentioned, the vector code is very like linear. You don't have branches, so it's some piece of code that you can actually optimize fairly well, even if you are just doing it
statically.
Statically, without exactly.
Okay, so what it means is with the JIT trick, you could actually go use more optimization routines, right? Because you have access to more than pure Java. This is what you are saying?
Well, I'm saying so. Currently, the Graal compiler doesn't support a few operations of the API.
But if
so
they are
if you go to the fallback, what we want to do is just implement a subset enough to run these models on GraalVM. And the next one is try to ensure that your vector code is compiled efficiently. Because, as I mentioned, there's a lot of caveats.
This is where you will have to JIT because there is no Java C compiler for that, right? This is why you will need to JIT because to native compile it. I mean, because my understanding is that you could use GraalVM, just instead of Java, the GraalVM 21, let's say, or 22, and then you could already use the vector API encoded in GraalVM, right?
No. So because the Graal compiler does not support enough features of the vector API, so the compiler cannot emit proper vector instruction.
Not yet.
That's the key. So,
but later,
because it's still a preview feature. So the vector API is still changing, and it's just a moving target. But as I mentioned, it already supports a very tiny subset.
Yes.
And I think if we add just a little bit more, just a tiny bit more, it can run these models
next weekend.
as fast or faster than
Alfonso. Next weekend is around.
Yeah. But this kind of changes require like deep compiler expertise. Let's say like I will leave my colleagues at the GraalVM compiler that just
I had already chat with GraalVM people about you, and they told me you are on different level. I was like, okay, as a level above. So I mean,
not really.
Okay. But still, let's say you have the features to run the matrix multiplications on GraalVM. Now we could just run it on, GraalVM without native compilation, right? We don't have to native compile it. So, but if we native compile it, what do we get out of that?
Right. So that's the next trick.
Yeah.
Maybe have you heard of Llama file? There's this other say attempt from attempt no, like this kind of a product from Mozilla and Justine Toney. She's the one that did this Cosmopolitan libc and these universal executables.
Hmm.
So she had this very interesting approach where you compile an executable that bundles in the executable also the weights. So you have a
Ah,
4 GB executable, right? And when you run it, it will spawn, like a server, and you can chat to the server and so on. So basically, it's a mix of Java, Llama CPP with the models embedded in the file, and it can run on Linux, Windows, Mac, and all these platforms. So we could do with GraalVM something very similar. And when I say similar, I would say maybe even better because it will be even like more seamless
hmm.
in the sense that you can pre-parse your model at build time,
Hmm.
and then by the time you run your model, you just need to memory map the weights, and that's it. And that will take like
Ah,
milliseconds. So you can start running inference. So you may think, oh, but the parsing takes nothing, but actually parsing takes from half a second to 2 seconds,
okay.
depending. So because it's single threaded, there's no way to parallelize it. But if you do the parsing ahead of time, so basically you parse all the vocabulary of the thing, of the model, you create the tokenizer beforehand, all the things that are fixed, and you always do the same thing again and again for the same model. You can actually start inferencing within milliseconds, and that's, I think, it's a very nice feature. And you can do it with very very minor modifications to the thing. So literally, you have like instant inference within Java, which is crazy, right? Because you would say, oh, but Java, it takes a long time to start, but with native image, you can achieve actually this.
There's a similar concept to what Quarkus does. I don't know whether you are aware of Quarkus. What they are doing, they have build time optimizations, and they just, for instance, reading XML configuration and generating bytecode, so you don't have to
Exactly,
do it
exactly.
again. And
So
this will be exactly the same, idea below, which is great. I mean, this will be the killer feature of native compilation.
right, so that will be one improvement we can have on native image. And then, for example, you can share the weight because they are memory mapped, so you only pay the price once, and you can have like multiple inference engines, like all like sharing the weights and all these kind of tricks. This is, of course, is not specific to native image, but I think the part where you can like instantly start inference, I think that's actually a very good feature, because not even Llama CPP, so all these other engines can do that, but we could do that with native image.
Yeah, this is I would say a double killer feature for native image, because the first one is it is as fast as Java or even faster, because there is no compiler optimization at runtime to expect, because just matrix multiplication happens in the vector pipeline anyway. And the second one is you could have build step optimizations, and
Exactly.
then you
Yes.
can ship three things. One executable, which is basically executable model. You get like yeah, right. So you can launch the model and you have complete app actually, which is huge. Actually, this is one of the killer features of native, because in my case, it's not always the case that native compilation is beneficial, because if startup times don't matter and memory doesn't matter a lot, then it depends, right? So, but this is one of the killer features. It's actually crazy.
Right.
Yeah. Yeah, pretty cool. But what I was surprised, you didn't mention the quantization. So I think Java, you're using floats or doubles? Floats.
Floats.
But the
Yes.
quantization means they use a float 16, right? I think. Or
Well, they have a custom, let's say, custom format for the quantization. So I'm talking Llama CPP.
Mhm.
So they can represent one weight with 1 byte, or even less, so four
Yeah.
bits only, and so on. So
Mhm.
they have these tricks. They like put a float and then some bits, and so it's a custom thing. So, but in our case, we run all the instructions or all the computations in float 32. For example, Llama CPP does, I think, in float 16.
Mhm.
Just as but I think that doesn't really affect
Okay.
the performance, because what so the hard part is actually unpacking the weights into the registers of the machine. So it doesn't matter if it's F16 or F32. So the costly part is actually reading the weights. So for example, if you have a one byte per weight, you need to like get it, so put it in a vector, shift it, multiply it, and cast it to a vector of floats, and that actually costs nothing. So the expensive part is actually reading the bytes to an actual vector register.
Okay. That's interesting, because I thought, with the Valhalla, I think they think about, have float 16, I think. So whether it could help or not, right? So
yes, so actually it could help, because right now you are kind of, so it's not only float 16, you have B float 16. So there are several formats going around with different pros and cons. And in Java, there's no way you have to get away with a short, right? And for example, if you want to multiply two float 16s, you have to convert to float 32, multiply, and then convert back. So on all this dance, I guess with Valhalla or some compiler in the VM specs can be augmented with support for float 16 or even any arbitrary value types that support all this operation in a fast way. Because again, you have to, right now it's annoying because of this. You have the conversions, they added the conversions, so you can convert from a float 32 to 16 and the other way around. But the multiplications, the sums, all this stuff is just, for example, there's no you don't have a vector of float. So in this SIMD operations, there's no a vector of float 16. So all you can have is a vector of shorts, of bytes, or float 32, but there's no float 16.
So this could help.
That could help a bit, yes.
Yeah.
Because then you could do twice as much operations, right? But as I mentioned again, the bottleneck is just reading from memory and not really the computation part.
Extremely cool. So what are your plans now for the next weekends? Or maybe even during your work. So hopefully the managers recognize what they have. And yeah.
So I think we are trying to, we submitted, I think, I'm not exactly sure, but an abstract for a talk at Devox, Belgium, I think, to talk a bit about this. As I mentioned, there is also a LangChain4j integration. This is not open source yet, but the idea is to make it open source at some point. And so basically, you can run all these models in pure Java through LangChain4j with different capabilities, because not all the models support all the features. But let's say they're good enough, for example, to run unit tests or so on. So for example, one of the issues with LangChain4j is that you have to either connect to a remote servers like OpenAI or whatever, or you can spawn a local something, for example, but you need to do, I need like a Docker container just to talk to do the inference.
Exactly.
But in this case, if you have a unit test or something where maybe you don't need to have crazy inference powers, you can get away with just running it in Java at a reasonable throughput.
Yeah. And I think if we can have the LangChain pipeline pure Java, and we are one step away with your invention, this is crazy, because then you can run in production without Docker. Imagine LangChain4j, I would like to go in production. So what I can do is I could just package the entire thing as jar, let's say, and run it whatever I like. But if this is remote, this is remote, I need some API keys, I can do nothing about that, but it will work. But if it's in Docker, it's painful. I mean, this is almost undoable. Because, if you are in the cloud, so you have your Docker and then another Docker, they have to talk, and two have to be, resilient and highly available, forget it. But if everything is in memory, it simplifies a lot.
Right. I think that's one of the cool features, that you can see through the boundary. So you can, the ways you can compress the state. For example, if you have a chat conversation, you can just compress it, store it to disk, and restore it later.
Yeah.
All these kind of features you can implement if you have these models implemented in Java. That this is completely opaque, and you cannot do this if you have you talk to some C code that is running on a Docker container. But yes, so I guess there's some value, as I mentioned, but it's not that you're going to chat with like GPT-4 or something with these local models. They are just like a tiny version of the big models. Just you can do certain tasks. You can actually do it even better, because you have a very good throughput And you can augment these models with function calling, for example. So you can give the model some tools to do some certain tasks.
Mhm.
And I think this combo is very powerful for some very specific tasks that you don't require any bigger, like, subscription or APIs or nothing like that. You can just run locally.
I think this is the future anyway, because I don't believe in the God models. I think the future will be of more specific models, If I would like to have a fraud detection, I get a tiny model which is very good just on fraud detection, but cannot,
Right.
tell me stories, or cannot, convert JSON to
Exactly.
CSV.
One case, for example, is spam detection.
Yeah,
So maybe you want to run
exactly.
spam detection on the client. You don't want to run it on
This
the
is what I
host.
actually am doing right now. And I'm not interested in ChatGPT 4. I just is good enough that it recognizes that the address is fake, it doesn't look right. And for that, I need a tiny model. And I would
Exactly.
like to run it on my machine. This is actually exactly what I'm doing right now.
Another example, for example, that I really like and I'm very impressed is have you tried the autocomplete, the line completion on IntelliJ?
Mhm.
So this one, because usually what you get is the copilot where just Inference will give you like a full snippet, but in IntelliJ, they autocomplete just the line,
Mhm.
and they guarantee that the line compiles.
Mhm.
And I think that's a very, very nice feature, because usually that's what you got, that's what you want. Just I want just to complete me the line in a way that it works,
Yeah.
that it compiles and so on. And I think that's everything runs locally. It's a tiny model and so on. But I think it's a very, very nice, nicely done, implemented feature.
Mhm. Also, something like how to call it, smart, almost like fraud detection, but parameter validation in projects.
Right.
If you get parameter from outside, you can be smarter. Now you have to implement null, not null, but you can say, okay, is it in range or whatever, and have smarter. So I think the future is bright for enterprise, and I don't believe the God models are, or how to call it, the really more powerful models. And I would say everything in the world becomes more specialized. It's not like we need to know. If you even think back, the servers, we got at the beginning a huge servers, and now we got mini servers, but more of them. And I think the same is true for models, that you get smaller specialized models, and then they can run locally.
Right. Yeah. So I also believe that there's some space for the smaller models, and you can arm or you can augment these smaller models.
Yeah.
And one of the things that you, for example, you want these models to recognize language or to have certain reasoning capabilities, but you don't want them, for example, or to waste space on the models knowing all the history of the humankind.
Exactly.
Or, like, for example, so you really want something that is capable of reasoning and following certain instructions, but doesn't waste any space or let's say
Exactly.
weights on like knowledge that you're not going to use.
Yeah.
For example, so. But that's very hard. How do you train a model that is able in language, capable of reasoning, but that have very little knowledge of the world, or at least of the training, the huge training sets? That's another topic.
This is where my knowledge stops, but maybe it's interesting, to remove some knowledge afterwards. They train it first and remove it later. I had no idea. Maybe way too hard.
So I try to look a bit around that, because really what I want is this one. So I want a model that knows language and nothing else. So it doesn't know, like, it doesn't have to know who Napoleon was or
Exactly.
whatever. But actually, that part of training and remove it later, I don't think is possible, because so ideally what you want is to never make the model learn those stuff. So only the abilities of language, but disregarding the actual contents of so some of the data. So don't memorize data basically. Anyway, I really like I'm like an enthusiast of this thing. So don't take my words as a thing, but I mean I think that will be very, very nice to like a huge step forward if you can have the reasoning part and the language skills, but not all the useless knowledge in the models.
Yeah. Perfect. So, fortunately, I will have to invite you back to talk about espresso. So there was no time this time, but I assume there are lots of weekends between. So you will, have LangChain for jailbreaking already. So, thank you for coming. Where people can find you on the internet and GitHub?
Yeah, so I have this GitHub/Mukel, Mukel. That's where you can find the Llama 3 repo and some other stuff. And you can find, I think, my Twitter, my LinkedIn there in the GitHub.
Mukel. I will also put it to show notes.
Okay.
Thank you for your time.
Yo, thank you, Adam, for inviting me.